In our previous videos, we have learned the theory on minimum potential energy, and we have learned the shape function, and also we have learned the strain displacement matrix. Those are the important tools to create or develop a new element. Now let's use those tools to create a beam element. Okay, so what does a beam element do? The beam element has a length and has two nodes, node I and node J. And each node will tell you two things. The movement perpendicular to the beam. In this case, the beam is going along X, so the movement is of two nodes is a Y. And then it tells you the angle, how much it turns, okay, along the on the node. Okay, we always because each beam has tells you four terms, right, for the movement on along y-axis for each node and the slope as well. So we have the element has four terms. So we the vertical displacement, we express that in a four constants, C1, C2, C3, C4. And we're going to define the slope based on the rise over run on this. So we take the derivative of the vertical displacement, which will give us an approximate value of the slope. Okay, let's solve for C1 to C4. So in when x is 0, okay, the displacement on I is UI1, and the angles on the node I is UI2, which is C2. Okay, nothing fancy. We just substitute x equal to 0 in those two equations. Now let's solve for x is equal to L. That's what happened at node J. Okay, and we will have these terms right here. Okay, we express these two equations into matrix format. These four equations, we put it in the matrix formats and take the inverse for that matrix. We will leave that Vx, and then we have a shape function developed. Okay, this is the shape function for the beam elements. Okay, we're gonna put that shape function aside. We're gonna approximate the movement along the y-axis. Okay, and we apply the bending theory. Okay, imagine the dv over dx, the small movement along the y-axis is gonna create some sort of movement along the x-axis, provided along the natural axis. Okay, these equations is all based on the bending theory. Okay, and then we want to find out the string relationship. So we take the derivative of ux, we get this term. Remember, the derivative of the shape function is a string displacement relationship. Okay, and we have matrix D, the string displacement matrix. We apply all terms in the minimum potential energy theory. We have these terms right here. Okay, each D is a 4 by 4 matrix. We take we multiply two matrices together. It's a lengthy process to multiply 2D matrix together. Let's do one terms right here, and then we multiply it and take the integral. So for the first entry, we have 12 over L cubed. Okay, and we repeat the same process for all other entries. Okay, this is the stiffness matrix of the beam elements. I understand the development of this matrix is kind of confusing, but if you do not understand the development of it totally, it's fine. But as long as you know how to use that stiffness matrix of the beam elements. The force vector for the beam elements is also quite tricky. Okay, we'll take the integral of the total work done along the beam. Okay, again we reapply the shape functions here. So that's the uniform load along the beam. Okay, we put that matrix, put the shape function matrix right here, take the integral of that from 0 to L. We have these 4 entries, which is the uniform load along the beam, and we express that in the force vector terms. In our next videos, I'm going to show you example how to apply those matrices. Thank you for your attention.